Okay, so now let us talk about the steepest descent method. So as we saw earlier, that if you have a CPP, then the things are pretty much easier because you have a KKT conditions. You have KKT conditions to find the optimal point. But it's not always easy to solve the equations. See, solving equations is easy sometimes because in academics we usually play with good equations. But when you don't have good equations, it's not easy to solve. We go towards the numerical methods. So numerical methods helps us to get the approximate solution. Okay, so here also we are going to see some of the numerical methods to find the approximate solutions. Okay, so among them, the first one is nothing but the steepest descent method. So before telling you this method, there are some things that I would like to tell you. So the first thing is, okay, so what is our problem? Our problem is the problem P. I have to minimize the function subject to the constraints gi of x bar less equals 0. And we have seen that if it is a CPP, then we have KKT conditions. Okay. And if not CPP, then what to do? Okay. So now see, for any numerical technique, what is the idea? Whenever you want to apply the numerical method, so suppose that x bar is the solution. If this is the actual solution of a problem or of a function, what do? We try to approximate. That means we construct the sequence of solutions x1, x, these are the approximate solutions. And we try to approach it towards the actual solution. So these are our approximate solutions. Okay, and we keep on taking the iterations or iterations. Okay, so x1 is one approximate solution. Then with the help of x1, we find x2, which is our second approximate solution. With the help of x2, we find x3. Okay, so once we have x1, with the help of x1, we do something and we get x2. Then what is x3? We get it from x2. From x2, you do something, you add, subtract, whatever. You do something to get x3. Then with x3, you do something to get x4. And these are the iterations we say. And the more iterations we do, the more closure, that means we approach towards x. The more closure we come towards the actual root because the error keeps on decreasing. So this is what usually the idea is. Okay, so whenever you want to find the you cannot solve analytically, you go numerically. That means you construct the sequence of approximate solutions. And that's what we do in numerical methods. So suppose you have x1, x2, x3, say xk plus 1. All these are what? These are approximate solutions. And we want to approach it towards x bar, the actual solution. X bar or x, whatever you want to say. You can say x bar as well, but doesn't matter. Okay. So, oh no, this won't be, these are the numbers. So let me just not write x bar. So this is the thing. And if I want to find any k plus 1th root, this is nothing but xk plus something. Now, usually what we do is there is something called as a step size and there is something called as a decay. Now see, now when you are in one dimensional space, when you are in just real numbers, if you take a point, you have only two directions. Either you can go to the right side or you can go to the left side. You have only two directions. As soon as the dimension increases, for example, say two-dimensional space, if this is a point x bar, I can, how many directions are there in which x bar can go? Obviously, you can see that there are infinitely many directions x bar can move. Okay, so I want to find xi's, which are the points actually. So it's x bar are the points, they are the optimal points. Okay, x bars are the optimal points. Sorry, not the numbers. They are the optimal points which we want to find. So x bar is here. Question is in which direction I should move. Once you have x1, question is in which direction I should move to get the best solution. So that is my dk. Dk is the direction in which I should go. And alpha k is what? It is the step size. What should be the step size? I should take optimal step size. So in that respective direction. so that I can approach to my solution faster. Okay, so xk is my previous solution, alpha k is the step size. Step size I should take to move in the direction dk to get the optimal solution. Okay, so usually this is what the technique is. So obviously now your question is, my xk can be one of the guess. Question is, once I have x1, how will I find x2? That means question is, what are my alpha k and dk's? This is what the question is. Okay, now there are some standard phrases that you may come across. So let me just state them. Let me just state the definitions. The first thing is called as a descent property. Okay, so suppose you have a problem P. What is your problem P? This is the problem P star. Okay, so when I will call a problem to be to have a descent property, if your f of xk plus 1 is less than f of xk, then I will say that f has a descent property, and you can say that as my k increases, this is less than, means I'm approaching towards the minimum value. Okay, because our problem is minimization problem, that's why this is a descent property. For maximum problem, there is something called as an ascent property. What do you think? When we say a function is having the ascent property, what do you think? What will be the sign?
Greater than x of
Greater
k.
than. Okay, good. Correct. Because for maximization, as we take new iterations, the value of function is maximum, right? So it has to be greater than. And for minimum, as we take x1, x2, x3, x4, as we keep on taking iterations, whatever x's we are getting, we want the minimum value of the function. Therefore, here it is less than. Okay, so let us just concentrate on less than. Equivalently, there is ascent property. Okay, so you know when a function has a descent property. Okay, that's first thing you might come across whenever you see a numerical technique problems. Second thing you come across is order of convergence. Second thing you come across is order of convergence. Now, what is order of convergence? Suppose your f of x, I want to find the root of this equation. Okay, now what do? You construct the sequence x1, x2, x3, xk, xk plus 1, and this is approaching towards x. Okay, what is my, if I take the length of xk minus x, this is some error. Let me call this as epsilon k. This is the error, right? Because xk is the approximate solution and x is the actual solution. So obviously the difference is nothing but the error. Okay, what will be epsilon k plus 1? It is norm of xk plus 1 minus x. This is the error between k plus 1 iteration and x, and this is the error between kth iteration and x. Now what do is, suppose there are two definitions I would like to tell you. So suppose there exists p and a positive and a finite alpha such that you have this condition, limit k going to infinity, norm of xk minus x upon norm of xk plus 1 minus x raised to p. If this quantity is finite, then we say that this the problem has pth order of convergence, and alpha is called as the rate of convergence. Okay, alpha is called as the rate of convergence and p is called as the order of convergence. And when your p is 1, we call this as to be a linear convergence. It converges linearly. When p is 2, we say it's a quadratic convergence, means it converges quadratically. And then p equal to 3, we say it's a cubic convergence. P equal to 4, we say biquadratic convergence. P is equal to 5, we say quintic convergence. In general, greater the value of p, faster your algorithm converges. Faster your algorithm converges. Now, let me just spend 1 minute or 2 minutes to just make you feel this sentence. Okay, I won't give you proof, but let me just make you feel this. Now see, the limit thing that I have written over here, what is this? This is epsilon k by my notation, and this is epsilon k plus 1. Oh, sorry, this is plus 1, and here it is k. Sorry, please make the change. In the numerator, you have xk plus 1 minus x, and denominator xk minus x. So with the notation, what is this? This is nothing but limit k going to infinity, epsilon k plus 1 upon epsilon k raised to p. This is my alpha. Another way to write limit is approaching this means what? Epsilon k. Another way of writing this is less equal sum m times epsilon k raised to p. Okay. So this is the bound I'm having. Now see, this is the errors. These are the errors. Those who have studied big O notation, small O notation, I don't know whether you have studied that or not, but if you have studied that, then you can recall this. Okay, connect with that thing. So what does it say? See, this is the error and this is also the error. This is the kth error, this is the k plus 1th error. This is the error which I'm getting after taking the latest iteration. This is the previous iteration ka error and this is the latest iteration ka error. Okay. Now here when larger the value of p, this decreases very fast. Okay, m is some constant. Larger, this is the error, very less, 0 point something, whatever. Now, larger the value of p, this will be very small. And therefore, this term becomes smaller faster. So, if larger the value of p, these terms become smaller faster. That means what? My k plus 1th error is very small. And whenever the error is becoming very small, it converges faster. Okay, so usually people just in the textbooks you will see this limit and they will say that higher the p it converges faster. Why that is so? Here is the small explanation I give usually, because one should feel that why the larger value of p implies that your algorithm is converging faster. Okay. So now just a homework, since you have already seen bisection method, Newton's method, Newton's method, just see what is their order of convergence. Does anyone know what is the order of convergence for Newton's method? Well, order of convergence is 2. Just see what is the order of convergence for bisection method or any numerical method. When you see, it's always good to know what is the order of convergence, because that will tell you which method is converging faster, and that will help you to choose a method when you solve a problem. Okay, so order of convergence is one of the important point that one should understand. Okay, that's one thing. There's another actually I won't be needing this in steepest descent method, but another thing that people uses or a phrase called as a unimodal function. What do you mean by unimodal function? If you have a function from AB to R. Okay, even just before that, make sure after the lecture you just listen to this once again. Okay, just listen this 1 or 2 more times so that the things become easier. If not, then you can ask me again. I will explain you, not an issue. Okay, when I will call this to be a unimodal function if it has only one peak. If f has only one peak. Okay, so for this is a unimodal function. This is a unimodal function. Okay, one peak. Ya to lowest point or the highest point. Those are unimodal functions. Okay, now when you have unimodal function, one can think of like, so if this is my x, a and b, so from a to x it is increasing and x to b it is decreasing. If you have unimodal function of this type, then a to x it is decreasing and x to b it is increasing. So there exists a point after which the nature of graph is changing. Okay, so such functions are called as unimodal functions. Now why unimodal functions are good to play with? Why they are good to play with? Because now suppose you take x1 and x2 such that x1 is less than x2 between a and b. Now see, you want to find the root. Once you have the interval, you want to find the root, that where my root will lie in this interval, whether it will be here, where it will lie, I don't know. Okay, so what interval should we choose? So that, or we need to decrease the interval. Now, I should decrease the interval from where to where? I should decrease the interval from where to where? That is the question. Okay, so once you keep on decreasing the interval, the more chances that you will get the good root. Okay, so when you have unimodal functions, things are very nice. Why it is nice? Because now suppose you have f is a unimodal function. Okay, since we are playing with minima, let me take, suppose it has a minimum something like this graph. Okay, suppose your f of x1 is less than f of x2. Then what can you say? Where the minimum value will lie? It will lie in which interval? That's what the question is. Let us try to understand this using graph. You tell me the answer. Okay. Now this is my odd interval of experiment. AB is the interval of experiment, and this is the unimodal function. Okay. Suppose my x1 is less than x2. This is my x1, then this is my x2. You can see that f of x1 is less than, so obviously this is my f of x1 and this is f of x2. So obviously my f of x1 is less than f of x2. So what do you think? What interval the minimum value of x will lie? Tell me the general interval. Where will the minimum value will lie? Will it lie in the interval a comma x2, or it will lie in the interval, definitely a comma b will be there, or x2 comma b? What do you think? In which interval you will have the minimum value? In which interval my function will have the minimum value? In the interval a to x2 or in the interval x2 comma b?
x2.
Correct, because you can see from x2 to b this is the value, but here you can see here somewhere from the graph we know that somewhere it will be here. So obviously it will be in the interval a to x2. Okay, so when you have a unimodal function where x1 is less than x2 and the function also keeps the same inequality, then you can concentrate on the interval a comma x2. Okay, because we know that, so instead of concentrating on a comma b, we concentrate on a comma x2. That's how we reduce the interval. Suppose we have that x1 is less than x. Suppose we have f of x1 is greater than f of x2. Then question is where the minimum value will lie. So let me draw the graph again because you can visualize the things very easily. This is A, this is B, this is x1 and this is x2. You can see over here f of x1 is bigger than f of x2. So what do you think? The minimum will lie in the interval ax1 or x1 to b? See, x2 can be here as well. Okay, so you can't say x1 x2 interval. Your x2 can be here as well. Your x2 can be here as well. But my f of x1 is bigger, that much I know. Okay, so it can't be here. X2 can't be here because my f of x1 is bigger than f of x2. But x2 can be any one of this point. So what do you think? Where will the minimum lie? In the interval ax1 or the interval x1b?
x1b.
Correct. It will lie in the interval. So now, if you have this condition, then we concentrate on this subinterval. Obviously, once the length of the interval decreases, your things becomes very good. I mean, you're happy that at least you have to work on the smaller interval. And suppose at those points the function is having the equal value, then the minimum will lie in the interval x1, x2. Why that is so? Let me draw on the next page. Let me call this as x1 and let me call this as x2. Okay, this is my A, this is my B. You can see that this is my x2. Okay, so you can see that at x1 and x2 function is having the same value and minimum is somewhere here. That means it is lying in between the interval x1, x2. So whenever you have unimodal functions, one can always reduce the interval of experiment. So that's why people try to see whether you have unimodal function or not. If it is not unimodal functions, then they try to restrict themselves. So if you have something like this, then they concentrate on this first interval, then they concentrate on this subinterval, then they concentrate on this subinterval. Because in this interval, yes, it's a unimodal function. Here also it is a unimodal. Here also it is unimodal. So that's why people are happy in playing with unimodal functions. And yeah, there's another reason that one should know unimodal function. Okay, so these are the basic things that one should know. Okay, now let us come to the steepest descent method. Remember our goal. Our goal is, so I told you what is a descent property. Okay, so our goal is, what is my alpha k and dk? I know that my xk plus 1 is xk plus alpha k dk. Okay, question is what should be my alpha k and what should be my dk? In which direction I should go? Okay, well, the answer is, okay, before telling you the answer, can you tell me what will be my dk? If this is my suppose xk, I know that I can go in many directions. Have you studied directional derivative concept? Do you know in which direction there is a maximum rate of change and in which direction there is a minimum rate of change?
Direction of unit vector, we have a maximum.
No, so the maximum, so this is the notation for
Direction of
directional
f
no,
maximum.
grad f. And minimum value is nothing but maximum is mod of grad f and minimum is minus mod of grad f, and this comes in the direction of grad f, and this comes in the direction of minus grad f. I will share my YouTube link with you. Just go through that lecture. Okay, so maximum value of the directional derivative is mod grad f at that point, and it occurs in the direction of grad f, and the minimum value is minus mod grad f, and it occurs in the direction of minus grad f. Okay, so after the lecture I will share the link, so you can just go through this. This is quite important, and because of this, your dk in this method, it is nothing but minus grad f. People will, when you see the books, they will say that choose or let your dk is equal to this, but many people doesn't say why. Okay, why? Because this is the answer. Okay, so dk is minus grad f because in that direction you will have the least slope. Okay, and since this is a minimization problem, that's why I'm going into the direction of minus grad f. It is maximization problem, we will go into the direction of plus grad f. Okay, so my dk is minus grad f, and alpha k, that is the optimal step size, you obtained by solving. So once I have dk, what is my xk plus 1? It is xk plus alpha k dk. So you just put in the function xk plus alpha k dk. This is xk is a number, dk is some number now. So once you put this value in the function f, your answer will be in terms of only one variable alpha k, and then one can use the single variable calculus. Okay, so that's what the rough idea is. Let me take an example so that this will be clear to you. Okay, so let us take an example so things will be clear to you. Example, let me take a function f of x1 x2 is equal to x1 square minus x1 x2 plus x2 square. Okay, and you have to find x1 x2 till what point, unless and until the difference between them, the error is less than 0.05, and take the initial guess to be 1 and 1 by 2. This is the initial guess x1. Now you have to find x2 x3 x4. Till what point you have to find? Till the difference, till the error is less than 0.05. Okay, so now I want to find x2. I know that my x2 is nothing but x1 plus alpha 1 d1. Okay, what is my d1? It is minus grad f. Can anyone tell me what is grad f? It is f with respect to x1. It is f with respect to x2. What is f with respect to x1? 2x1 minus 2x1
x2.
minus x2. And what is f with respect to x2? Minus x1 plus 2x2. Okay. So what is grad f d1 at 1 comma half? So minus of 2 minus 1 by 2 comma minus 1 plus 1, and this implies that your d1 at the point comes out to be minus of 4 minus 1 3 by 2 comma 0. So therefore don't write this. Okay, so let me just repeat whatever I am doing. So first step, I want to find x2. I know by descent method it is x1 plus alpha 1 d1. What is d1? It is minus of grad f. So you find grad f, you take minus sign, and at the point 1 comma half, you find the d1, which is minus 3 by 2 comma 0. Okay, so we get d1 to be minus 3 by 2 comma 0. So d1 is minus 3 by 2 0. Now question is, what is alpha 1? So what is my x2? It is x1 plus alpha 1 d1. Just understand this, and after the lecture make sure you solve it on your own also. You simply add them up, you get this vector x2. Now what the method says, you find f of x2 and then find the optimal alpha 1. So what is my f of x2? Now this x2 is x2 bar. Okay, so what is the function? My function is nothing but x1 square minus x1 x2 plus x2 square. So this is my x1 x2, small x1 x2. This is my capital X2. This is a vector. Okay, so what is that? X1 square means 1 minus 3 by 2 alpha 1 square minus x1 x2 plus x2 square. I want to find alpha 1, the optimal alpha 1. How do you find optimal value in one variable function? Now you can say this is a function in one variable. I can write this as f of alpha 1. This is 1 minus 3 by 2 alpha 1 square minus 1 by 2 minus 3 by 4 alpha 1 plus 1 by 4. Now this is a function of one variable. How do you find the optimal value? Can anyone remember how do you find optimal value? You take the derivative, equate it to 0. Correct? So what is this? 2 times 1 minus 3 by 2 alpha 1 into minus 3 by 2. Here this is plus 3 by 4 equal to 0. Okay, so alpha 1 comes out to be 1 by 2. So your x2 is nothing but x1 plus alpha 1 d1. My x1 was the initial root which they gave 1 and 1 by 2. Alpha 1 came out to be 1 by 2. And what was your d1? d1 came out to be minus 3 by 2 comma 0. And therefore this is nothing but 1 minus 3 by 4, and this is 1 by 2. And this is nothing but 1 by 4 and 1 by 2. This is my x2. Now should I go for x3? Let us check what is f of x2 and let us see what is f of x1. If this is less than 0.05, then stop. If it is not, then you have to go for x3 as well. Okay, but here, well, I have done the calculation for you. So here, when you do this f of x2 minus f of x1, the difference will come out to be 0.75. Okay, what is the function over here? Your function is this function. So you put 1 and 1 by 2, that is your f of x1, and then you find f of x2 and you take the difference, it will come out to be 0.75, which is not less than 0.05. So you need to find x3 as well. What will be x3? x2 plus alpha 2 d2. What is x2? x2 is 1 by 4, 1 by 2 plus alpha 2. What is d2? It is minus grad f at x2. Earlier it was minus grad f at x1. Now it is minus grad f at x2. Okay. So when you do this thing, this quantity will come out to be 0.3 by 4. You also do the calculation. If you get something different, let me know. And your alpha 2 will come out to be 1 by 2. Okay. So once you have this thing, your x3 will come out to be, you just do this later on, let me not waste time. Your x3 will come out to be 1 by 4 and 1 by 8. And now when you find the difference between f of x3 and f of x2, the difference will be, it will come out to be 9 by 64, which is less than 0.05. Okay, so this is how you can use this method to find the approximate answer. Okay, so I hope the idea is clear. So once x1 is initial guess is given to you, you find x2 by using x1 plus alpha 1 d1. x1 is given to you, your d1 is minus of grad f at x1. Using that and alpha 1, you need to find alpha 1. You put in the functional value to find the value of alpha 1. So you find the value of alpha 1 by doing all these things. Once you do these things, you get the value of alpha 1, then you find the value of alpha x2. Once you have x2, you check whether the difference is less than 0.05 or not. If yes, well and good, you stop your process. If not, then do this.